In this video, we're going to look at the image again. The image of a transform is the set of all output values. So members of the output set where there exists some input. For some input value, I can reach that output value. What we're going to claim in this theorem is that the image of L is a subspace of W, not just some random set, which is what this says, but more specifically a set that's closed under addition, closed under multiplication by scalars, and contains a zero vector. So again, our criteria for a subspace is that the image of L contains the zero vector in W, because the image of L is about points in the output space. And so if we just think about our W space here for a moment, and we think back to the transform, if I have the 0 point here, how can I map to the 0 point there? Well, we know this from linear transforms. If I take a 0 in the input space, it always maps to the 0 in the output space. We proved that earlier, that for the 0 vector in the input space, the transform of that is going to equal 0 in the output space for any linear transform. And therefore, there is an input that maps to the output 0 value. So 0 is an element of the image of L. So we're asking, is the image of L a subspace? Well, that subspace has to contain the 0 vector, and it does. The second criteria is that the image of L must be closed under addition. And again, the routine for this is let's pick two elements of that set. We know those are in the set. Let's add them and make sure the sum is also in the set. So consider W1, and it's going to be in the image of L, and W2 also in the image of L. What do we know about those? It means that we know V1 and V2 exist such that V1 and V2 are in the input set, V, and that L of V1 equals W1 and L of V2 equals W2. So if I pick any two values in our output set that we can reach, they're in the image, so W1 and W2, the reason they're in the image is because there were precursor vectors over here that led to W1 and W2 with the transformation L. All right, now our question is the sum W1 plus W2 in the image of L? We just grabbed two random elements of the image. If I add them together and get a third point, is it also in the image? What does it mean for W1 plus W2 to be in the image of L? Well, let's consider the transform of V1 plus V2. So go back to the input space. What about V1 plus V2? Well, we know that because L is linear, that's equal to the L of V1 first plus the L of V2 by the linearity of L. And we know that these two vectors here were selected because they add up to W1 plus W2. And since V1 plus V2 came from the input set, they are card-carrying members of the set over here. We should label that. And L of V1 plus V2 is equal to W1 plus W2. That means that I can add my two output values from the image and get another image value. W1 plus W2 is also an element of the image of our transform. So it is closed under addition. Take any two vectors in the image, here and here, add them together. There will be a precursor back here somewhere that when we transform it gives us the sum. Last but not least, we need to show that our image of L is closed under scalar multiplication. Under scalar. So consider W, which is in our image, and some alpha, that's a real number. What do we know? We know immediately, because W is in the image, that for some V, which is in the input space, When we run that through our function, we get W. Again, if we have our two sets, W and V, we run our transform on those. If I say that W is in the image, little w, then that's because there was some little v that mapped to it through our transform. Well, next up we need to show that, or test whether alpha w is in the image of L for any alpha and any w. Well, of course it is, because we got these linearity properties. Let's consider the transform of alpha v. Why would you consider that? Well, because I can bring the alpha out front by the linearity of L. And if I can do that, well, I also know the transform L of V is W. That's the whole point of W being in the image. And so we get alpha W, and that means since L of alpha V equals alpha W, and alpha V is in the input set, right? I had V, but if I scale it, I'm also staying in V because V is a subspace. Then alpha V is in V. That's the definition of being in the image. Alpha W is in the image of L. When I scale V to alpha V, I'm going to get alpha W as an output. And that means if I know W is in the output, I'm guaranteed that any scalar multiple of it's also going to be in the valid output set. And those are our three criteria for the image to be a vector subspace. And so the image of L, satisfying all three criteria, is a vector subspace. Again, of what space? Well, we have two. We're talking about the output space here, W, specifically a vector subspace of W. Again, could be the whole thing, could be a single point, but it's going to have that subspace structure as part of W.